Okay, so yeah, we're back, and today we're going to talk about some application of magnetism. So let me start off with the loudspeaker. Now for the loudspeaker, right, what we have here is a permanent magnet over here, the one that I'm going to highlight in blue. This is the permanent magnet, alright, and what we have on the other component is a speaker cone, which I am now shading in yellow. Now to better visualize this, right, they actually have coils of wire over here, so it's quite around the speaker cone, the one in yellow. Okay, so let's call this a cone. Okay, and what's happening in the wire is current is actually flowing, and current is actually flowing in this direction. Okay, such that on this region here, current is going in, and on the other region, let me draw it in green, it's actually going out. Okay, so yeah, so you have to visualize the current direction. Okay, now with this current direction, we can actually use the right hand grip rule. Okay, so current going into the page on the right side of the cone and coming out of the page on the left side of the cone. And what we have after we use the right hand grip rule is that we have north here and south here. Now when this happens, I think it's very obvious. What's going to happen next is an attraction between these two, right? So attraction will occur, and when the entire thing is being attracted, what will happen is this entire cone will then shift downwards. Okay, now how does shifting helps? There's actually a thin piece of membrane over here, and when the cone shifts, the membrane will vibrate, and the vibration of this membrane will actually cause sound to be produced. And in a nutshell, that's how the loudspeaker works, or at least the first step. Now when this happens, after the entire speaker shifts downwards, right, so the speaker shifts downwards. Okay, obviously it can't shift down all the way, so if it shifts down all the way, then the speaker gets stuck. Okay, so what's going to happen next is that this current here, they're actually alternating current. Okay, in other words, the direction of the current will change, and if the direction of the current changes, we know that this polarity here it changes according to how the current changes direction, right? So the polarity will change according to how the current changes direction, and this will actually affect this part. So it actually gets attracted or repelled accordingly, right? Of course, this attraction or repulsion should follow the law of magnetism. Okay, and the law of magnetism states that like poles will actually repel, and unlike poles will actually attract. Okay, and yeah, so this is how the loudspeaker works. Okay, so if we go to the question, okay, over here we have another question. First thing first, we have to identify what the question is talking about. So this our coil of wire. So wire is actually strapped around the plastic cone. This is the permanent magnet that's held in place. Okay, so over here what we have is current into page, current out of page. Okay, so remember, X is always inside. Okay, so it's always going inside, it's going into O. Okay, as the letter O stands for outside, right? So it's always going outside. Okay, that is going to the out of page. Okay, so just remember, O stands for, the dot stands for outside. Outside means it's going out of page. Okay, so current is coming out here, Okay, so I can't draw an upward arrow. Okay, so you have to imagine. Okay, so this is kind of like coming out, right? And there's another region here where it's actually going in. Okay, so it's actually a coil of wire that's strapped around, okay, and behind. Okay, so if you use your right hand grip rule, okay, so it's coming in, going out here. Okay, so sorry, a bit confusing, right, if I draw it that way. So let me draw in the proper direction. So it's coming out and going inside here. Okay, coiling around. Okay, coming out, going inside here, coiling around, coming out, going in, coming out, going in, coming out, going in, coming out, going in. Okay, use your right hand grip rule. Okay, you'll get that the current direction should be in this manner. If the current direction is in this manner, then the north will be on the left side, right, using your right hand grip rule. So magnetic field always points from north to south. So okay, yeah, so because they want the magnetic field, right, so you can't just label N and S, you need to draw the magnetic field. Remember to draw at least 3 lines and label your arrows. Okay, now what is meant by a frequency of 150 hertz? Because it's alternating current, 150 hertz would mean that the direction changes 150 times in 1 second. Okay, now so the movement of the coil, okay, we have to, this is a 3-mark question, right? So first thing first, the movement of the coil. Now when the coil is north and this is south, what happens is a repulsion. Okay, but of course when the current changes direction, the polarity changes as well, and then you have attraction. Okay, it's exactly what we talked about earlier on the black screen. Okay, so what will happen to the coil? The coil will actually move back and forth towards the magnet. Okay, so let's answer the question first. It moves back and moves back and forth towards the magnet. Okay, now we need to say why, right? So there are 2 reasons why. Okay, first reason, I'm just going to write in point form. Okay, so the first reason is that because of the current, okay, current actually creates a magnetic field whose direction can be determined using the right hand grip rule. Okay, now using right hand grip rule we can determine the magnetic field, but that's not enough. Okay, so still doesn't explain why it moves back and forth. Okay, so the second point is the law of magnetism. Okay, law of magnetism states that blah blah blah, like poles repel, attract when they are unlike poles. Okay, so this part I leave it to you. You should know what's the law of magnetism, and therefore when a coil has a north polarity near the magnet, it repels. Near the magnet, okay, it actually repels, and of course the converse is true. Okay, so you may want to write when coil has a north polarity near the magnet, it repels, and when the current changes direction, it will induce a south polarity on the coil, okay, nearer to the bar magnet, and this causes an attraction. Okay, so that's the main answer. Okay, okay, so question 3 asks now one of the main word over here is this phrase over one of the main phrase here is the phrase large current. Okay, so what happens when a large current passes through this entire circuit breaker function? Okay, so what happens over here is whenever there's current flowing through this soft iron core, okay, what happens is it becomes an electromagnet. However, when a large current flows through it becomes a stronger electromagnet. Okay, so when a large current flows through it becomes a stronger electromagnet, and what happens is that this iron lever here will be attracted to the coil. Okay, now when this iron lever is attracted to the coil, although the diagram looks like this part over here is detachable, it is not detachable. Okay, so it's actually one whole piece of metal. Okay, it is not detachable. So when this entire thing moves to the left, okay, what happens is we have this, I'm going to highlight in red, we have this entire mechanism moving to the left. Okay, and as you can see, if this entire thing moves to the left, this piece of rectangle block over here will be not in contact with this triangular block over here, right? And when they're not in contact, what you have is out of contact. What you have is a open circuit. Now it's functioning as like the doorbell. Okay, so if you know how the doorbell works, this should be a breeze. Okay, now when it's out of contact, what happens is this becomes this will stop being an electromagnet, right? And when you stop being an electromagnet, this thing won't be attracted. The spring, right, will actually pull it back to its original position. Okay, so that's how this circuit breaker works in a nutshell. Now the answer is actually quite straightforward. Okay, so I'm just gonna write in point form, and I think you guys can phrase your answer from there. Okay, so the first thing first, we have to mention that the soft iron core will be magnetized. Okay, or a better word is actually not magnetized but induced to be an electromagnet. Okay, so use this phrase over here, induced to be an electromagnet. Now when this happens, right, we have to say that this attracts the iron lever, and what happens next is which pulls the metal bar, and this results in number 3, contacts not in contact anymore, right? And this actually creates an open circuit. Then number 4, spring actually okay, and that is why the circuit breaker has to be reset. Now every time we reset, what will happen is we're actually resetting this spring, and when we pull the spring, right, the spring actually pulls this entire thing back. Okay, so I'm going to draw in blue. Okay, when we pull this thing, okay, so that there must be a switch over here, right? So you go to your circuit breaker box, you pull that switch. Okay, what happens is that we are actually pulling this string, we are actually pulling this spring. Okay, and when we pull the spring, right, the iron lever that was attracted previously will actually move back to the right. Okay, and when it moves back to the right, the entire circuit will be working again. Okay, so that's how it works. The large current in the circuit is cut off. Describe what happens to the soft iron core and iron lever. I think we already mentioned. Okay, so I'm not going to mention again. Basically, iron core loses magnetism, it falls back to its original position. Okay, and why is it not advisable? Okay, now we have, every time this comes out, you have to differentiate. You have to know that they are actually talking about temporary magnet versus permanent magnet. Okay, now obviously we do not want a permanent magnet here, right? We don't want the iron lever to be permanently attracted to the soft iron core. That so much so that even after we press the switch, right, for it to go back to original position, because this is permanent, okay, because this entire thing is permanent, it will be attracted again. So we don't want that to happen. Okay, so if we use a steel core, okay, the contacts will forever be in contact, and with that, right, we won't achieve this. What we want to achieve is an open circuit. Okay, but with a permanent magnet, we will not be able to achieve this open circuit. We will, with the permanent magnet, we can achieve the open circuit, but we will not be able to achieve a closed circuit anymore, and that's not what we want. We want it to be back to a closed circuit after everything is back to normal, right? Okay, it only functions as an open circuit when there is large current. Okay, so that's the purpose. Okay, we don't want it to be an open circuit whenever there is a current. That's not what we want. Okay. Now, as I mentioned in class, if the question has the word force, you skip the entire question, so we're going to skip this. Okay, over here, I think it's quite straightforward. I went through this in class. Again, there's the word steel bar, okay, suggesting that it's probably a question on temporary magnet and permanent magnet. Okay, just to make things clear, direction of current flow is the conventional current. Okay, so dotted means the wire behind, right? Okay, so if you use your right hand grid rule and identifying the current direction, okay, you actually get your north over here. Okay, remember that magnetic field always goes from north to south. So if you were to draw the magnetic field line, it should be like this. Sorry. Always goes from north, so it's coming out from north. Okay. Yeah, so imagine north is here somewhere. Okay, so it's going into south. Imagine south is here, so it's going from north to south. And that brings me back to question 1. I think I made a mistake. Yeah. No. Okay. Yeah. Okay. So magnetic field is always going from north to south. Okay. But if it's going from north to south, it's always coming out from north, going into south. All right. Okay. Once again. Oh. Okay. I'm so sorry, but in this case, right, what will happen is that X and Y will actually experience a force, and with that we actually skip this question too. So let's skip, and we'll just finish up one last question. Now this is a question on magnetic field. Okay, so solenoid X and solenoid Y, obviously solenoid Y has more ion fillings, right? So with more ion fillings, it means that this has greater magnetic field. Okay, the word B field actually means magnetic field. Now if this has more ion fillings, then we say that this has greater magnetic field, and greater magnetic field is linked to greater current. Okay, so answer B, Y. Okay, yeah, this can be determined using the right hand grid rule. Okay, and this also can be determined using the right hand grid rule. Okay, this is in my notes, so I'm not going to go through. Now I'm also not going to go through question 8. It's a question that I went through in class. Okay, so same thing, iron rod, 2 iron rods are placed. Okay, then they are replaced with an aluminum rod. Okay, now I need you all to go to your notes and look at aluminum rod. Is it a magnetic material, or is it a non-magnetic material? Okay, so I think the answer lies there. Now the 2 rods move away from each other, suggesting a repulsion. Now only magnets can repel, so these 2 rods must be magnets. Okay, now lastly, let me just go through the last question for this video, which is question 7, right? Okay, so question 7 shows a simple moving iron ammeter, suggests why the needle deflects with a steady current when a steady current flows through the coil. Now when the needle deflects, right, okay, so it can either deflect in this manner or in this manner. Okay, however, we need to know this is a soft iron, not a magnet, right? So only magnets can repel. So obviously when current is coming through the coil, okay, it actually induces a magnetic field here, right? It induces a magnetic field, and when it induces a magnetic field, this entire thing functions like a magnet. Okay, so you can treat this as a magnet. Now when this thing functions like a magnet, what happens over here? Attraction happens, right? Okay, but I need you all to also remember that if I have a magnet, okay, let's say this is north and this is south, and I have a nail here, right? What will happen to the nail? Will the nail be able to attract another nail? Yes, and this is what we call it as a magnetic induction. Okay, and therefore this will be north, this will be south, this will be north, this will be south. Okay, let me draw in red to make it better. So this is north, this is south. Okay, so what happens here? We call it magnetic induction. So there's a few parts to your answer, so let me just give you the answer. Okay, So first thing first, when current flows through the coil actually is induced to become an electromagnet. Okay, so you can say that, or you can say that the coil produces a magnetic field. Okay, either way, it both suggests that the coil becomes a magnet. Okay, so I'm just going to write here, when current flows through coil, okay, coil becomes magnetized, right? Okay, now as coil becomes magnetized, what happens? It actually induces the soft ion core to be a temporary magnet with opposite polarity. Okay, now this induces the soft ion core to be a temporary magnet with opposite polarity. This is important to suggest that they will attract. Okay, since unlike poles attract, it will attract the soft ion. Alright, that's 3 marks. Okay, now will the direction of the deflection change when the direction of direct current is reversed? Now if this direction is reversed, okay, so previously, let me draw in black. Maybe this is north, this is south. If this is north, then this is south, then this must be south, and this must be north. Now if we change the direction, I'm going to draw in blue. Okay, obviously if you change the direction, the polarity will change. Okay, so let's call it S and N. Okay, as written in blue. Now if this is S, then this is N, then on the soft ion bar, on the right side it will be north, and on the left side it will be south. Okay, why? Then you refer back to here. Okay, if this bar magnet is changed from, okay, sorry, if this bar magnet is, I'm drawing black, if this bar magnet is changed from south to north, and the polarity is reversed, obviously this will be reversed as well, right? So the same goes for here. Okay, so maybe in the previous case, here, let me rewrite everything. Maybe in the previous case it was from north south here. Okay, it will induce a south and north over here, but right now it has changed so that this is north and this is south, and it will actually induce a north and south over here. Okay, so this is the idea. The ink is not very thick. Okay, let me just rewrite it. Okay, so this is for the iron and this is for the coil. Alright, so will the direction of the deflection change? No. Okay, why no? Because same thing, it induces the soft ion core to be a temporary magnet with opposite polarity. So this is true for magnetic induction. Okay, and therefore it will not repel back, it will just continue to attract. Now if you have replaced the DC current with an AC of 25 Hz, okay, even though the direction of this coil, right, it will continue to change. It changes according to this 25 Hz. That means it will change 25 times in 1 second. However, using this principle, induces a soft ion core to be a temporary magnet with opposite polarity. Every time it changes, every time the coil changes direction. Okay, so when coil changes direction, change direction. Okay, this means change, right? When the coil changes direction, okay, induces opposite polarity on soft iron, right? So because it induces opposite polarity on soft iron, it will be attracted. Now, however, things can be different if there's a permanent magnet here. If there's a permanent magnet, if this is, instead of soft iron, it is a permanent magnet, right? What will happen is that there will be attraction and repulsion. Every time this is north and this is south, depending on what the soft iron is over here, it may be attracted, and then so that when it changes to the next polarity, it will be repelled. Okay, so if this is a permanent magnet, then yes, If it's a permanent magnet, then there will be a repulsion and attraction. Okay. However, in this case, this is a soft iron, and because it's a soft iron, it follows this idea that is going to be induced opposite polarity, and because of that it will be attracted. Okay, it will always be attracted because of this idea that an opposite polarity is being induced on it. Okay, so I'll end the video here. I hope this helps, and roughly this covers quite a few applications of magnetism. Just try to make sense of the mechanism whenever something comes up. Okay, maybe a plastic cone, our loudspeaker may not come out, or maybe circuit breaker may not come out, maybe something else new comes up. You just read the question, and using the idea of this right hand grip rule, using the idea of magnetic induction, should be fine. Okay, so I'll end the video here. Thanks for watching. Bye.